So last time we defined heating set, or alternately black box PIT. So this is ideally it should be a small set, so poly-sized in the parameter which is size of the circuit S. So that many points in the full space f to the n, such that so we'll say the H is a heating set for a family of circuit C if for every non-zero circuit C in the family there is always a point alpha bar in H such that C doesn't vanish, right. So in this case we say that heating set, this set H hits C. So the first point is whether a small heating set exists, right. Why should it exist? Because if the field is infinite, then size S circuits are actually infinitely many. So why should there be a finite point? Infinitely many polynomials will have infinitely many roots overall. So why should there be a finite set of points each that are non-roots? So intuitively the reason is that I mean, if you do a simple back of the envelope counting, then you will see that the number of circuits although is infinitely many, but the effective dimension, so if you look at the number of free variables in your circuit, they are only S, because you have only S edges, and on these S edges you will put S constants. So in a way, if you think of each of these unset variable on the wires, which will later on be fixed as constants, this degree of freedom is only S. So formally we can define it as the dimension of some variety.
Don't you have to first talk about the universal circuit, and then, because the structure of the circuit is not there.
But we have done enough structural theorems to get to that. It's a log S depth alternating addition multiplication gates tree. So for that tree you want to just fix the constants. So by dimension arguments you can actually show that there is always a small set of points which will be able to hit all possible circuits of sizes, whether the field is finite or infinite. That will not matter, because it mainly depends on the degrees of freedom that you have, not on the actual number of circuits. So we will not formally do that. A simplified question is there in the assignment for finite fields, because the dimension argument actually requires algebraic geometry if you do want to do it precisely. So that is beyond the scope of this course. But for finite fields you can do a simple counting. You can actually count the number of circuits that will be finite and compare that with the number of possible zeros and show that there is a small heating set. So existence is shown by the dimension of circuit families, dimension of the circuit family. Which we will leave for now undefined. Just intuitively whatever you think of dimension geometrically. Yeah, and by Schwarz-Zippel you can do something. By Schwarz-Zippel you know that if you just pick a random A in S to the n, where S is big enough, S is basically more than the degree of the circuit, So by Schwarzschild, you know that if you pick a random point, then it will be able to hit. Right. So this basically shows that there is a hitting set of size 1, right? Does it show that? Not quite. No, here is the statement. A random A bar will hit a given circuit. So if suppose you had assumed that this field is finite,
The statement should be.
the field is finite, suppose. So size of F is, let's say,
I mean, the order of quantifiers, like here for every circuit, like a random A bar will hit it, but that does not mean that there's a single A bar that will hit every circuit.
yeah, so this is hitting only 1. That is true.
Hitting will be high, but there's many, so it
Hmm.
will be 0.
Right.
Unless your class C is bad.
Yeah. Yeah, so this probably was not a good idea. Let me skip this part. The correct lemma statement is given in the lecture notes. So actually this has to be corrected by saying something more. So you also need the field to be finite so that you can do a counting. So assume a finite field so that you can actually count how many circuits there are. And second thing you will need is, from this you will have to deduce, from the above statement by Schwarzschild you have to assume deduce that hitting set of size poly S will suffice. So not just one point, but if you take enough points bounded by poly S, then they will be able to actually hit all these exponentially many circuits. Yeah, but I will skip the proof of this. I think something more interesting is asked in the assignment. So with that, all these other statements will imply. So the question that is of interest and that is open is the following. It's not about existence, but it is about actually constructing or designing a hitting set. So this is also called de-randomization question of PIT. So in fact, to be precise, black box PIT. So can a hitting set be computed? Given 1 to the S parameter, size parameter. So can a hitting set be computed in deterministic poly S time? Okay, so this is the question which is open, the keyword being this determinism. So you know that these hitting sets exist, and you know that there is a practical way of generating them, but the questions which are open is how do you design it in deterministic polynomial time, right? So remember that designing also means verifying. So not only you have to output a set of points, but you also have to be there should also be a proof that this is a hitting set, right? You cannot just randomly guess the points and make a claim that this is a hitting set. You have to give a proof of it. So verification goes with this. So provably, this should be done provably. So it's a design and verification question. or you can just ask whether black box PIT is in P. It's the same thing. Okay, so alternately these are the two algorithmic questions, they are equivalent. It might be easier to show that white box PIT is in P, but that is also open. Okay, that is a question of lesser interest. Although if you have done the course 640, there we prove that even if you do white box PIT in P, it gives you lower bounds. So that has complexity lower bound consequences. So in that sense, even white box is interesting. A side remark, we will not go into that. We will only study black box PIT for now. There is an equivalent concept. So instead of thinking of a set of points, you can actually use interpolation and look at a single point. Okay, so given this hitting set H, so by interpolation using a new variable t, okay, so introduce a new variable t and use interpolation. So interpolation just means that you have these set of points H, look at the first coordinate of all of them. So these are just field points, field elements. So design a polynomial, let's say P1t, such that P11 will be the first number, P12 will be the second one, and so on. So P1t will produce all these values, okay, sequentially. Now you may be working in a finite field, so you may not have 1, 2, 3, but whatever. So you just pick field elements and some sequence of them, and P1 in order on these points should evaluate to your first coordinate of points in H. That is what is meant by interpolation. So what will be the degree of P1?
This is the hitting set generator, right?
Yeah, so what you get is called a hitting set generator, because it's a single function which can produce not only points in H, but infinitely many points. I mean, you can just keep evaluating it and you will get newer and newer points. So what is the degree of P1? What does? No, not unique. So no. So it will be equal to size of H.
I mean, it's a bit weird, right?
No, it's not weird. We want P1I to be the ith point's first coordinate.
Right.
So it will actually be the size of H.
I see.
We don't care about what exactly the values are. We just care about sequence matching. So by interpolation we can find polynomials P1, let me use y instead of t. P1y, P2y dot dot Pny, and we'll call this vector of polynomials Py. Right, so what we have done is P1y interpolates on the first coordinates of H, then P2y interpolates on the second coordinates of H, and so on, such that their first few values on fixing y from F give us the points in H. So you should just think of the values of this vector of polynomials as reproducing the hitting set points. If the field is not closed, so I mean for in this definition actually you can even take the field to be smallest, size 2, because you can ask y to be fixed in f bar, algebraic closure. So algebraic closure is always infinite. So irrespective of what the parameters are, you can always look at just this single vector py such that on some given sequence of field elements it will evaluate 2 points in H. It will reproduce the points in H. So it's an easy thing to show that degree of pi for every I is at most the size. So number of points in H. Is that clear? So hence interpolation motivates the definition of hitting set generator. So this motivates us to define a arithmetic analog of something which is studied in Boolean world, which is called pseudo random generators. So have you taken any course in PRG? Not yet.
Seen them in your course,
Okay.
the previous one.
So PRGs is something older than algebraic complexity. It's already a fundamental concept both in cryptography and complexity theory. So pseudo random generator. So obviously we don't have constructions known for optimal PRGs. So PRGs, I mean in cryptographic terms, these are again multi-valued functions which will actually take a string and it will stretch it to a bigger string with the guarantee that this bigger string will look more or less random. Okay, so now defining this more or less takes a lot of work, so I will not mention that, but it's something which you also want in algorithms when you want to flip a coin, right? So a computer flips a coin using these PRGs. So there are no proofs that thing being used is a PRG, but it's basically a heuristic function which is employed in practical algorithms, but the abstraction of that is exactly PRG. So PRG may be outputting a single bit, and generally it might be outputting a string, and usually it is used to stretch strings. And then you can compare these questions. Many of the questions are actually equivalent. So this is a whole area. So hence this HSG is not really unmotivated. It is analogous to what was being studied already. So let us define it. So P1y dot dot Pny, let's put n in the superscript to signify that it's an n tuple. So this we are calling Py, and this whole set we are calling P. So this set P is called, set of tuples is called an S of n HSG right? So that's a heating set generator. So this in a way is also stretching because it takes y and it stretches it into n tuple. Right? So this is also stretching, and what should S of n signify? So there are two resources. How big are these polynomials? Degree. And second more important resource is the time taken to produce them. So Sn will signify both. So it's called an Sn HSG against some family, against circuit family C. So recall that circuit family will have polynomials f sub n for n variate, right? So this is also an infinite family. And what should happen? So respectively p n y, or let's put n on top. So p super n should be a heating set for these Fn. So let's write that down. If each p j n y has degree less than equal to S of n. S of n is a function in it's a function on n. So each pjny has degree Sn and is computable in some polynomial in the degree time. Okay, so for example, motivating case will be take S of n to be n to the some constant. So we are saying that the degree is small, and also it can be computed efficiently. Now computation obviously means that in pjy you will have many coordinates, many coefficients. So these coefficients are integers, and you want to compute them in bits, right? So the whole polynomial should be computable in polytime. So this is I mean, here when we say time, we really mean bit operations, right? Every bit should be computed. It is not like algebraic complexity where we'll ignore the constants. If you actually ignore the constants, then these questions become trivial. So it's not that easy. I mean, you actually want to compute all these integers in polynomial time. And second is, of course, for all non-zero C in your family, let's say it's n variate, Cn at this Pny should be non-zero. Is that clear? So efficiently computable tuple of polynomials such that every non-zero circuit, when you substitute this tuple, it evaluates to non-zero. Is it clear that if there is an HSG, then there is also a heating set? So why is that clear? So Sn HSG against C implies heating set against C of size. So how much will be the size? Yeah, so
Coordinate is like finite fields, or
there is a technical.
the field is finite?
No, nothing to do with the field. So somebody has given you an SN HSG, right? It's a powerful thing. Doesn't matter what the field is. So Now hitting set, if the field is too small, you are free to go to an extension, but then you have to actually output points, not a polynomial. So you have to output n tuples with the coordinates as constants, not polynomials, right? So yeah, so if you look at this red part, you have to look at the degree of y in this. So degree of y in this is bounded by Sn times the degree of Cn. So that many values of y you have to substitute. So it will be of size Sn times degree of Cn. So that's an additional technicality. It's an important technical point because if your family has exponential degree circuits, then these two are not equivalent, right? Because dec Cn is exponential, so you are getting a hitting set of exponential size, which isn't a big deal.
But HRG is against that particular circuit, right? So it cannot have a very huge degree here.
Cn is a circuit in your family. If you are looking at size as circuits, the degree can be s to the s, 2 raised to s. But as long as you are in VP, it's equivalent. So for VP where the degree is also restricted, we are fine. Otherwise, there are some technical points, but it's not very important for our lecture or even interest. So this will quickly give you the equivalence. So from hitting set you can go to HSG by interpolation, and from HSG you can go to hitting set by evaluation. So this is morally correct. And so now the open question becomes, do efficiently computable, so do efficiently computable right. So this is the question equivalent to, is black box PIT is in P. Yeah, so currently this is a big open problem, even in complexity theory. The reason is that, so apart from being a natural or basic question, this is also related to proving lower bounds, circuit lower bounds. So close to VP different from VNP. Okay, so PIT results are basically, you can think of them as algorithmic results, but interestingly you can also view them as trying to prove circuit lower bounds. And the better hitting sets or HSGs you can generate, the stronger lower bound results you will get. Okay, so existence of an algorithm is connected to non-existence of algorithms, right? That is the flip connection. So any questions till this point? Okay, so there is an advanced result which I can just, it takes several lectures to actually prove this in CS 640. So it's a result by Carbonetes Impagliazzo. So they showed that if PIT, which is white box PIT, if you find an algorithm for PIT, yeah, this P is actually quite strong. So the result will even work if, sorry.
You mean like NP or something, right? I think we had this discussion.
Oh, I'll give you n sub x.
The proof that we saw in the previous course, will that work for n sub x?
Yes.
Works for NP, but
Do it as an exercise. Yes. So if you can improve PIT to a PIT is in BPP. It has a randomized polynomial time algorithm, but that doesn't mean that it is in NP, and that also doesn't mean that it is in non-deterministic sub-exponential time. But it does mean that it is in NEXP, right? In fact, it is in EXP, because exponential time, obviously, you can just open up the circuit and check. So it is in EXP, it is in P space, but those things don't imply that it is in sub-exp or even n sub-exp. So if you prove any of these cases, then what you get is NEXP is not in P/poly. Yeah, so if you don't know what is P/poly, this is basically a Boolean analog of VP. So in VP we are looking at algebraic circuits. In P/poly we are looking at Boolean circuits. So Boolean means that you are just computing a Boolean function using AND or NOT gates. It's again a tree. Yeah, and it's a kind of, in many ways it is incomparable, but sometimes we also try to put artificial comparisons. But in many cases it's an incomparable word, because we cannot say anything about the depth. There is no result on depth reduction. But we have these simple observations that you can assume. So you have now three kinds of gates. So even the alternating thing is not very clear, but you can at least say that if there are two layers, both are the same, then you can merge them. So you have AND, OR, and then you have NOT gates spread around, which probably you can bring to the bottom or the top. No, not the top, I think bottom. Yeah, so you can do these simple things, but other than that there is not much structure. In algebraic circuits we have seen far more powerful structural theorems. But what we are saying here is something very much believable, because we are saying that this in particular, it doesn't tell you anything about NP. So NP may or may not be in P/poly, which means satisfiability may or may not have small circuits, but NEXP will not have small circuits. So NEXP has a complete problem which is called succinct 3-sat. So succinct 3-sat will not have small Boolean circuits. Okay, this is the Boolean, you can say Boolean circuit lower bound, but it doesn't stop here. It's an OR condition. So either this or VNP different from VP. Okay, so this is the full theorem. So it says that if you have a white box PIT algorithm or something far weaker than that, some non-trivial white box PIT algorithm, then either you will prove a Boolean circuit lower bound or a algebraic circuit lower bound. So either way, PIT is related to lower bounds. Is this clear? So proving this actually requires a lot of work, which we cannot do here. But if you are interested, you can follow lecture notes of CS 640 and then ask me questions. So let us just skip this proof, because it actually, believe it or not, it will go through PRGs, although in the statement you don't see any PRG. I mean, in fact, in the statement you don't see any mention of randomization, but still the proof will actually go through PRG, which is a bit unsatisfactory. But anyways, that currently I think is the only known proof. So we skip this proof and instead focus on black box PIT. So we focus on the implications of an efficient HSG. So what is the relationship between black box PIT and lower bounds? So obviously, because of this result, there will again be a lower bound connection, but the proofs will be a bit easier, and they will definitely be all algebraic. There will be no Boolean stuff involved. So we'll try to complete that. So for HSG, there are some older results from the 80s due to Heinz and Schnorr. In the 80s, but we will just follow more recent version due to Agarwal. So we'll prove two things. So first we'll show that if there is an efficient HSG, then you get a lower bound result. And in the second theorem, we'll show that if you have a lower bound result, then you can design non-trivial HSGs. Okay, so HSG is kind of equivalent with lower bounds. Let F be an SN HSG against some family C. Okay, so we want the HSG to be non-trivial, so it is fair to assume that Sn is not a very large function. Okay, it is smaller than 2 raised to n by 2. If Sn is 2 raised to n by 2 or bigger, then it's not an interesting assumption. You are picking a very large, very bad hitting set. So then there is no reason to expect that you will get lower bounds, because it's a trivial hypothesis. So let's assume that you have an interesting HSG against C. Then there exists a multilinear polynomial So there exists a polynomial which is computable in poly Sn time. So what do we mean that a polynomial is computable in poly Sn time? So the polynomial will have exponentially many monomials. We don't want to compute all of them. So we are just talking about our favorite coefficient. So somebody gives you a monomial and asks for the coefficient. So that can be computed in poly SN time. Okay. Obviously, if you want to compute all the coefficients, then it will take 2 raised to n time. So we don't want that. We just are saying that coefficient can be computed in this polynomial in poly SN time. That is not in C. Okay, so there is a polynomial that is kind of explicit. So this is the explicitness part, but it is outside the circuit family C. Okay, so that's a lower bound. Is that clear? So this is the strength of an HSG, or the implication of an efficient HSG. So if you have an efficient HSG against some circuit family, then what you will get is an explicit polynomial that is outside your family. So any idea how you will show this? So this actually has a very simple proof, right? What is the proof? Sorry?
You can interpolate.
I wouldn't say interpolate, I would say the opposite. Well, I would say
I mean, make sure that your polynomial has all of these as the roots.
yes. So yeah, so which should be called compute the annihilator,
You're interpolating.
the coefficients.
Yeah, okay, yeah. I mean, it just depends. Heinz and Schnorr give like an algebraic geometric proof, right? They still
No, they have two results. So Heinz and Schnorr showed that very small hitting sets exist and are even computable in P space. And second part of the paper actually does this, which is so hitting set generator is just a sequence of univariate polynomials. It's a tuple of univariate polynomials. So you basically find an annihilator that will be n variate, and when you feed this HSG, it vanishes, right? So if your polynomial is vanishing at the HSG, it means what?
It's not in the circuit.
It cannot be in C. So that's it, that's the proof. Well, so you have to implement this idea. So some parameters are involved, and also you want a very simple polynomial, you want multilinear polynomial. So let's do that rigorously. Well, and also you want it to be explicit. So why am I claiming that annihilator is explicit, right? So those issues we have to work out. So consider the HSG P1y dot PNY say for large enough n, just to avoid border cases. Well, so and so we want a multilinear annihilator. So if it is n variate, you will have how many monomials or coefficients? 2 raised to n, right? So these 2 raised to n things are your unknowns. You want to find them. Yeah, that may not be enough to motivate, but somehow that exponential is the reason why I'll keep a log here. So log of S of n, and m is So this will be the number of variables in the annihilator. Okay, so actually I will need to construct this hard annihilator. I'll use only around log of Sn many PIs, not all of them. So I'll only use these many, because so the point is that these first m PIs which I am using, this already gives me 2 raised to m unknowns in the annihilator. And what are the constraints? How many constraints are there? So let's do that comparison. So the idea is to consider an annihilator Q x1 dot dot xm for p1y dot dot pmy. Say this annihilator is it has coefficients Cs, Xs, right. So this is just the monomial. So since we wanted a multilinear annihilator, so the monomials which appear are just, they are in bijection with subsets of 1 to m. So they are 2 raised to m, and Cs is the unknown coefficient. These are the unknowns which we want to find, and which we want to find in a it should be explicit. It should not just be random fixing. So such that Cs is in the base field and Q. Yeah, so I have been calling Q annihilator, which means that when you substitute P1 to Pm, what happens? Yeah, so that is the cardinal equation. So remember this equation, that Q vanishes at the point at the substitution P1 dot dot Pm. P1 to Pm are given to you by an efficient algorithm. Q is a very long polynomial and its coefficients are unknown. Actually it is not. So how long is it? How many unknowns are there? Only 2 raised to m, right? The way we have defined 2 raised to m is around S of n, and so assuming that S of n was something efficient, Q actually doesn't have too many non-zero coefficients, so we can just find all of them using some linear system solver. So this red box actually gives you linear constraints in C. So you solve for C.
So the explicit description will just be the coefficient vector.
Right. So you compare on both sides coefficients of x bar.
Right. I mean, the solving part does not have to be efficient, right?
Sorry, no. After you substitute, it becomes a univariate in y. So you compare y monomials both sides. P1 is in y, right? This is in y.
Oh, but now that the y degree can go up, right?
Yeah, so let's write that down. So this sets up a linear system in the unknown Cs. So let's compare unknowns with constraints. So how many unknowns are there? So unknowns are well, exactly they are 2 raised to m many. And how many constraints will you get from the red box? Number of linear constraints.
Product of degrees of y1 to ym. That will be the
Yeah,
degree
so
of-
what is the degree of y in the LHS? So this is well, it is bounded by S of n. It is bounded by S of n times the
degree of y.
degree of q. No, S of n is the degree of y in P1, and then
Degree of q is like m, right?
degree of q is m. So Sn times m. Exactly. Okay, so if you have a linear system which is, by the way, homogeneous. Why is it homogeneous? Yeah, because if you look at the definition of Q above, in every monomial you have an unknown setting which is CS. So it's a homogeneous system. That gives you a homogeneous system. So in a homogeneous linear system, you have number of unknowns more than the linear constraints. So 2 raised to m is greater than equal to S of n times m.
Because
Why this? Yeah, so let us check this. So 2 raised to m is Sn square, and S of m is what was m? 2 log Sn, right? Yeah, so with the right n, you will get this as greater than. S of n will be greater than 2 log Sn, right? So this is quite safe. This is why we needed a big enough n. Sn is a growing function, of course. So this will ultimately happen. Right, so the number of unknowns is more than the linear constraints. So which means what? It's a solvable system. Right? There is always, in fact, infinitely many solutions. So since number of unknowns is greater than number of linear constraints, there exists a solution for CS. There is a non-zero solution. And it is computable in how much time? So this is a 2 raised to m cross 2 raised to m matrix, right? This linear system. So polynomial in that much time. And probably you cannot do any better than 2 raised to 2m. Right? That's a lower bound for solving this system. Okay, so hence Q exists, first of all, and secondly, Q is not in C, because if Q was in C, then Q at P1 dot dot Pm cannot vanish, right? That was a HSG. And third is any coefficient in Q is, so Q is m variate, right? It's Qm, Q sub m. It's M variate. So when you when you ask for a monomial, its coefficient is computable in poly 2 raised to m. Right. So we say that this is E computable. So E is a class just below exponential time, where you can solve. I mean, the problems which are in E are those that are solvable in 2 raised to big O of n time. N is the input size, right? So QM is of that type. You ask for a monomial, the coefficient will be outputted in 2 raised to order m. Right, so you have a E explicit polynomial that is hard for C. Right. Is there any questions about this proof? It's a simple proof, but there are these parameters and there are some interesting specializations of this theorem also. So currently we were taking C as just some abstract complexity class, but you can take C to be, for example, size S circuits of degree S. So if you do that, then what happens? What do you deduce? So take C to be size S, degree S circuits. So if C has a poly S sized HSG, poly S HSG, then what do you get? So consider the proof which we just did, right? So the M will be around log S.
S log S, right.
Yeah, so you will get a annihilator which is a hard polynomial that has log S, around log S many variables, and it is computable in poly S. It's poly S computable basically. Its coefficients are poly S computable, and finally it is not in C, which means that this log S variate circuit, its circuit complexity is more than S. So it is actually exponentially hard. So then there exists a QM. So it has many properties. So it is QM is multilinear. QM is 2 raised to big O of m computable. And QM is 2 raised to omega m hard. Okay, so you have this amazing polynomial construction. So it's a E computable, exponentially hard, multilinear polynomial. Is this clear? Yeah, so this specialization is my favorite, but the previous theorem actually gives you always a polynomial that will be outside C. If you have an HSG for C, then there is a polynomial outside C, which is also explicit. But this really is the motivating case for doing all this. So if this is clear, then let us try to study the converse of this. So if you have a QM like this, can you design a heating set generator for VP? How do you do that? Oh,
We did this, right?
where?
Previous course?
Did we? There was no algebraic complexity. I think I avoid using even algebraic circuit as a term.
You avoided it a lot.
Yeah.
then we must have used the design for something else, right?
Yeah, no, because of PRG. Nissan Vigderson design is actually, I mean, it started with PRG. Yeah, right. So that is the historical motivation that in the Boolean world, there is a strong connect between PRG and lower bounds, Boolean circuit lower bounds. So hence here also you would try to prove a strong connection. So one direction we have shown. So this we can call HSG to lower bound, HSG to hardness. Let's say. And the converse question will be hardness to HSG. So if there is hardness, then can you design HSGs, which is also called sometimes hardness versus randomness. So if hardness is there, then randomness cannot be there. And if randomness cannot be there, then hardness is. So it's equivalent. Is there a converse? For example, does VP different from VNP imply efficient HSG for VP? Yes, so such a strong thing we will not prove. We won't be able to show that efficient HSG is something as powerful as separating VP from VNP. That also doesn't happen in the Boolean world. So P not equal to NP is not directly connected with PRG construction. Okay, so P not equal to NP is a hard or at least incomparable question with constructing PRGs or de-randomizing VPP. But we'll get close. Okay, so we'll get very lower bounds which are close, and if our HSG is very nicely behaved, then we can even show that VP is different from VNP. Okay, but I will not go into those properties. So we'll prove a weaker claim. So, okay, I think our time is nearly up. So let me not give the formal statement, just mention that assuming this QM existence satisfying these three properties, tomorrow what we will show is an HSG which is not as good as poly S, but as good as S to the log S. So if there is a hard polynomial, then if there is hardness, then there is a nearly polynomial time, so quasi polynomial time HSG. Okay, so this will be a very close converse.